Hello and welcome to the fourth and last session of our Formula Student Workshop series here at SimScale in collaboration with Formula Student Germany. Yes, today we are really on the final straight, and before we start to talk about design processes, I would like to make sure that everybody can hear me loud and clearly. So in the case you can hear me, guys, please click the raise your hand button so I know that everything is working fine. Oh, great. I see a lot of hands and a lot of names I already know from the past session. Great. So in the case, for some reasons, the audio stream should drop, you can also use our toll-free audio service numbers, which you will find right now on your screen. Okay, then let's get started with our today's topic. And first of all, let's take a quick look at our today's agenda. So the subject of our today's session is the design process itself. So we will not talk so much about how to create a good CFD simulation, but mainly how to prepare everything you need for a CFD simulation, starting from CAD, and also we want to show you later on during a live design study how you can use CFD to optimize your car, and therefore we tested several front wing designs in the last days, which we will share with you. Just after this, I will present your homework assignment to you, and finally, I'm very proud that Nicholas Perrin will join for a live Q&A. Where you can ask him all your questions. Nick is really well known in the motorsport industry as a pioneer for design processes and also for motorsport business modeling, and I'm very happy that he agreed to share his knowledge with you. Okay, let's quickly talk about some important organizational things related to this workshop series. Basically, this is the final session, so there's not a lot of we have to talk about. Today, as I mentioned, Nick will join us. We changed a little bit today's curriculum due to several requests from the audience, so we will not talk so much about track aerodynamics since we did it last week and focus more on model management. Yes, and another guest joining today is my colleague Akram. I'm very happy that Akram found the time to help us out here. Akram will just introduce himself, but some words about him. Akram is very young, but already he is really a top expert for CAD pre-processing and motorsport aerodynamics. And yes, I'm very happy to give the floor to Akram. Akram, can you hear me?
Yes, I can hear you. Can you hear me?
Yes, we can hear you perfectly. Great. So I will just make you to the presenter 1 second.
All right. Okay, so please can you hear me if you can see my screen?
Everything is working fine, Akram.
Okay, perfect. Then let's start. Okay, so good morning, good afternoon, good evening, wherever you are around the world. Welcome to this last session of our workshop series, Formula Student Aerodynamics. We have covered a lot of application during the last few sessions, and today we will talk mainly about pre-processing and how you can handle the geometries, especially because Formula students' geometries are really complex geometries, and there is a lot of things that we have to talk about to make sure that you will be able to run high fidelity simulations. So brief introduction about me. So my name is Akram. My full name is Mohammed Akram Mufok. I'm user success engineer at SimScale with aeronautical engineering academic background, and I do have extensive experience in working with several CAD softwares and CAE applications, and mainly my application in the field of CFD. So let's move to the agenda. So I've decided to split the presentation into 3 parts. So first of all, because we are going to talk about how you can handle geometries and so on, so it's really important to understand the different types of the geometries that we have in the CAD softwares. Then we'll go to the problem that we will face later when we start to design using the CAD software. And finally, finally, we will talk about cleanup, and also we have a case example that we did here during the last time to show you how you can redesign the front wing of a car, and we will talk about this later in more detail. So let's start. So first of all, maybe you have already worked with CAD softwares, and you know that when you work with CAD, there is two different approaches in CAD, or two different representation in the CAE and the CAD field. So first of all, we have the precise surface, and we have also the tessellated surface. We're going to talk about more details about what's the difference between the two surfaces or the two representations, but in the same time we will talk about how we can handle the two different representations. So let's start with the precise surface. So the precise surface is the CAD representation of the surfaces. Primarily, we have two types of surfaces. So we use regular surfaces and freeform surfaces. So when you design in your CAD, so most of the CAD softwares, they work with this technology of the precise surface. And what you can do with the regular surface and the freeform surfaces, actually here we have some examples to illustrate what's the difference. So in this slide we can see some type or some different examples of regular surface. So here just in the right or the left corner on the top you can see this extruded surface, which is like really the basic example to show the case of regular surface just by having a profile extruded along a path or along direction to be right. So from this side we have the sphere, so it's also really a basic shape to describe it with a regular surface. Also we can describe with the regular surface cylinders as well and rolled surface, but for the rolled surface, because there is two types of rolled surface. Sometimes we can have, for example, in this model that we have here, we have three profiles connected together, but sometimes we can add the tangency in the profile, so we will have more like lofted surface along different profiles. Let's move to the second type of surfaces that we can find in the precise surface. It's the freeform. So the freeform generally based on a nerve surface or nerve representation, which is based on a couple of splines that are combined together, and based on the splines, I'm going to show you in the next slide what means spline. We'll have this distribution of the parameters along the splines that we can get this shape. So as you can see, the freeform surface will give you like really more freedom in your design, and this will, of course, parameterizing freeform surfaces is a little bit difficult or much difficult than the regular surface, but this can give you more creativity in your design, so we can have different designs than just regular shapes. So here we can see, so to give you an idea about what's the nerves representation, so here it's the nerve surface, and the lines represented in red are the splines that control the surface. So when you move this the red points, you will move the surface because the surface it's just a function of the position of these points. So the format that supports the precise surface, usually we can find the STP or STEP, or also there is another format called the FTP, are not the same. Also we have the IGES, BREP, and the native CAD formats, because every CAD software has its own formats. So let's talk about the second type of surfaces, which is the tessellated surface. So the tessellated surface, it's surface representation using identical elements, triangles, quadratic. Generally we use these two types, but I don't know really if there is a polyhedral representation. Maybe we can talk about this later, of the elements. So as you can see here in this picture from the side, this is an example of tessellated surface. So it's combination of many, at least one or two elements, and can be like millions, that will describe the distribution of your surface. So for the format that support the tessellated surface, usually the most used, and maybe if you're working with sim scale, it's the most common surface file format that we will face, it's the STL, and we will talk about the STL format later. And we have also OBJ, or there is other surfaces, there is other files that can support the tessellated surface as well. So here we can see a comparison between a precise surface that we can see here in the number 1 figure, and we see from the other side we have 3 other surfaces representations, but we are talking about tessellated surface here. And as you can see here, the precise surface will give you really an exact representation of your shape. So you will, for example, if you're gonna model a sphere like this one, you will get really accurate result of the sphere, because you will just put some parameters and you will get your surface based on these parameters. But if you will go for the tessellated surface, so the figure 2, 3, and 4, what we can see that the accuracy of the shape is described by the number of elements that we have on our shape. For example, if we take the example of the figure 2, we can see that the surface is not really representing sphere, but it's kind of weird shape. It looks like approximately like sphere, but it's not really accurate. So we have to make sure when we work with tessellated surface, we have to make sure that in the curvatures, in the where you have like not regular shape, you have to increase the density of the tessellation of the surface there. For example, if we take the idea of front wing or any wing, for example, in the leading edge, you have to increase the tessellation of the because you have the curvature. Otherwise, you will have really weird shape that will not represent the real geometry that you want to do. So we have to make sure when we work with tessellated surface, we have to increase the tessellation. So here it's really important because during this workshop you will work with STL files and you will edit the STL file. So I think it's really important to understand how the file is built inside and how the geometry itself is built. So like I told you, so the geometry is built based on many elements, and every element is represented by 3 components, three vertices in the space. So like you can see here, the V mean vertex, and we have 3 vertices to represent like triangle. And of course, if you have quadratic representation, you will have 4. And also, we need the 3 components in the space of every vertex, so for 1, 2, and 3. And also, we need normal that will represent the direction of the surface. Well, like you can see here, here we have an example of the file format. So we have here the file will start with solid and the name of the solid, then we'll end with end solid name, and inside, in between the start and the end, or the name of the solid and the end of the solid. So you will have first of all the normal of the surface, then you will have outer loop, and you will get the 3 components or the 3 vertices with the 3 components in the space, and you will end with end facet. Then this will represent one surface. And of course, if you will have 1 million or a couple of thousands of elements in your geometry, so you will repeat this until you will have the whole geometries, then you will end with end solid and name. Okay, so let's talk now about, because usually when there is no software, when you model, you will start with tessellated surface. So any software, when you start modeling with it, you will start with a precise surface. And of course, later you will convert, because usually we, in CFD or in other softwares, they don't support so many formats, so that's why there is some special formats that you can use everywhere. Now, one of these formats is the STL, and it's really good formats to handle, especially if you have high quality surface. So when we start from precise surface, from the point of CAD, so when we design this part, so we can actually convert the precise surface into tessellated surface. It's possible to do this step in any software, in any CAD software available in the market. So any software can do this step of converting the precise surface into tessellated surface. But the reverse, it's not possible. So we can't, so if you have already an existing tessellated surface, you can't go back to the precise surface. And it's not possible because when you do this, when you create your tessellation, you will lose the representation of the NURBS representation, and you will not, and you can't back to the other point. It's possible sometimes. What you can do, you can convert every triangle to a single surface, but this will not work. So the geometry will be not that good. So you have to make sure that or you have to remember that going from precise surface into tessellated surface or converting to the tessellated surface, it's possible, but from tessellated surface to precise surface, it's not possible. So here we have, I have already mentioned this before, but here just some formats that you can find in the two different categories. So for the precise surface, we have step format, we have IGES, we have bunch of formats that you can find over there in the precise surface. And for the tessellated surface, you can find STL format, OBG, other formats as well, but these are the most used formats like in the engineering field and especially in the business in this field. So here we can see some like advantages and disadvantages of the STL format. So the problem, so let's start with the advantages first. So no conversion errors, what it means. So when you convert from precision surface to tessellated surface, you will get high quality surface, especially if you like tune a little bit because any software will give you the possibility to tune some parameters of the tessellation when you want to move from the precision surface to tessellated surface. So it's possible. So high flexibility. This means you will have like a model that you can tune it. You can of course later for the pre-processing there is a lot of functions of filling holes, and I'm gonna talk about this later, but there's a lot of functions in the pre-processing that you can do it on STL files in a really perfect way. So it's suitable for automation. So when you want to, for example, especially when you want to do automatic design space exploration, or I don't know, the STL format is really good to do this work, and it's really flexible in these points. But of course, nothing is perfect in this world, so we have advantages and we have disadvantages. So the loss of the technological, topological, informations, restricted editability, so you can't, so when you create the STL formats, you can't edit this model, so you will not, so you can't add, for example, a fillet or any other operation, or maybe you can add more material on top of the STL. So when you create the STL, you can't go back to the editing phase. Okay, so let's move to the next point, which is the most important point for you today, because the first, what I was talking about is just like an introduction to put you in this thing of different files and formats, but now it's the really important thing. So CAD problems. So maybe you have already designed some geometries, and when you move directly from the CAD world to the CAE world, and especially in CFD, there is a lot of things that you have to take in consideration, and we're going to talk about this in the next few slides. So why do surfaces need to be prepared? So anyone who worked with CFD before, when you get like direct model from the CAD, it's really difficult sometimes to put this model directly in the CFD software and start doing your mesh and start running your simulation. So first of all, you have to go through this really important part, and at our days in CFD, pre-processing is really the most important part, because the solvers, approximately all the softwares have the same solvers and so on, but the pre-processing is the most important thing. And actually in the industry, the pre-processing is the part that takes the most of time in the design process or in the simulation process, because there is a lot of work have to be done in this phase. Like I said, when you get directly a model from CAD, you have to take in consideration some constraints that you have to do. For example, like intersection, like there is a lot of problems that we will see now. So why surface need to be prepared or repaired for the simulation? So first of all, sometimes the imported CAD has too many details. So for example, if you are going to take like full car model so this CAD is mainly for maybe construction or something like that, you will find a lot of features and a lot of elements that we don't need actually in CFD or in our simulation, because these details will just add more complexity for our geometry but will not have so much effect on the results, and sometimes create some problems for the mesh generation. So we have to take this in consideration to create high quality mesh. Another possible problem is surface errors that we can find on the, so these are the most common problems, but of course there is too many other problems that you can face in the CAD. So first of all, volume is not closed, and this is the most important thing that you have to take in consideration when you start doing your simulation in the pre-processing stage. So you have to make sure that your model is watertight, and I'm going to show you why your model has to be watertight. So sometimes we can find some problem of surface discontinuity. Maybe when I'm talking like this, you will find these things a little bit complex, but I'm going to show you this in slides. And we have surfaces intersect between each other. And to illustrate this, so we have here in this slide some figures that we can explain the idea in more detail. So first of all, let's start with from the left side, intersection of surfaces, and this is like the most common problem in CFD. And me personally, like I've never worked in simulation without facing this problem. So when you CAD, sometimes you have to trim two surfaces with each other, and sometimes you forget, or sometimes how to say, like the constraints in the CAD are not really tuned, so sometimes there is an intersection between the two surfaces, and this will create problem later for the mesh generation, because sometimes the software or the algorithm of the mesh generation cannot really understand which surface had to be meshed and which one will be like cut from the geometry. And this is really important to take care before starting doing your simulation. So intersection problems are really common in the geometries, and you have to take to make sure and to take care about this point. But actually sometimes it's can be helpful, especially when you work with the snappy hex mesh. And for our platform at SimScale, we are using snappy hex mesh technology. So sometimes it's important to have intersection. For example, I'm going to put it as a note, and I'm going to talk about it later when I will get this picture of the front wing where you have to take care, so you have to take the intersection in consideration, because the software sometime or the algorithm of generation generate the mesh cannot really understand which point have to be measured and which surface have to be cutted. And like I said, sometimes it's important to have intersection. Another really important problem that you can face, and this problem can like really ruin everything, it's the open volume, or if the volume it's not watertight. So if you can take a close look to this geometry here in the middle, you can see is like, in this point we have like a cut in the geometry, and in reality this cut does not exist, but sometimes when you work on the CAD, sometimes you will lose some points, I mean some edges to select, so you will have some open open surfaces or holes, or sometimes this can happen also when you do the translation from, or the conversion from a CAD software or from the precise surface to the tessellated surface. So this problem sometimes can happen, and the problem that will occur if you will have this kind of problems is that you will have some cells that will escape inside the geometry and will give you like wrong results in the end. Because, for example, if we can imagine that this part here in reality it's not empty inside, so we make it empty just because we want to do simulation. So we have to make sure that the volume inside is the volume is closed, and we will not have open surfaces like this or holes in the middle of our geometries. Otherwise we will find a lot of problems. One other really common problem that we can face in the CAD, and this problem is mainly a consequence of CAD. So it's not when you convert your geometry. So this mainly can happen in CAD. Sometimes when we create like two surfaces, or we create like two surfaces and we want to do a loft surface between the two surfaces, sometimes, so we can just imagine that this one from the left side surrounded by the blue line, it's a separate surface, and the one surrounded with the green lines, it's another surface. And sometimes the surfaces are really close, but in reality they don't intersect, and this gap can create the same problem like the open volume, that you will have some cells that will escape here inside. And so first of all, you will have like bad mesh, a mesh that will not predict your real physical problem, and also in the same time you will have some problems here of the cells that they will escape inside. Okay, so let's move on. So now we have we got an idea about the problems that we can face in the surfaces, but in cleanup or in the pre-processing, because the pre-processing actually it's not only meshing, but it's cleaning up and meshing and applying boundary layer, applying boundary condition and so on. So the second part, so when you make sure that you have clean geometry and so on, so we will not have this kind of problems that we have seen before, it's really important to defeature your model. And what I mean by this, so here in front of us we have two pictures. So from the left side we can see this model. So from here, from this vision, we can't see really the details, but we're going to go to details and you will see the difference. So here we have the construction model, because actually CFDs or CAD is not only used for like CFD to create models for CFD, but CAD can be used in many different applications, like creating models for understanding like how you will build your model and so on. So there is a lot of things. And here we have two types of CAD models. So we have construction model, which is like looks like this one, And the CFD model, or with other words, we can say CAE model, because we can use it for different applications of CAE. So let's go in the details and let's take a look from the front to the back step by step, and we will see what's the difference between the construction model or building model and CFD model. Because when you CAD these two models, you have to take in consideration completely two different approaches. So the first one, the construction model, you have to make sure that your system is accurately represented. There is a lot of components that you have to assemble together. You have to make sure that the assembly of the whole car is well represented. But for the CFD model, there is other considerations like really watertight geometry. We will not have a lot of details in the geometry, and let me show you here more details to illustrate what I'm talking about. So as the previous slide, so from the left side we have the construction model, and from the right side we have the CFD model. And let's take a close look just here to this beam here, or I don't know what's called, we can call it maybe pillar or element for support. So this element will support the front wing with the body of the car. And as you can see here, for the construction model, there is a lot of details that that are already in the model, like some elements of connection, so a lot of mechanical elements that if we want to do simulation with this model, first of all, this model is really detailed. So we need to make sure that we have really fine mesh to capture all these geometries and all these details in the body and the front wing and here this element. So first of all, we will have really 10 times or more cells invested in this model to really get accurate simulation. But the most important thing, because we have all these elements and all these details, so sometimes we'll find the problems in the mesh that the mesh cannot really cover all this geometry because the angle, maybe it's really sharp. Maybe if we can take a look here inside, we can see that the surfaces are really sharp and maybe the mesh cannot get there, and then you will have problems. So you will not predict your geometry in the right way, and this will create a lot of problems. But for CFD, you can see that all these elements have been cut off and the model is really clean and smooth. Of course, let's make sure one thing is when we do this defeaturing or reducing the details of the geometry, this of course will have an effect of the flow field later, but the benefit is because you're not gonna like run one simulation to optimize your car. You're gonna run a couple of, I don't know, hundreds or maybe thousands of different geometries. So as the first step, it's really important to make smooth, clean, good watertight geometry, and you will accelerate the process of your design. Then what you can do as a final step of validation of your results, you can take the last design and add all these details, but it's not recommended. Also in the industrial field, of course, they take some details, but not to the really detailed elements like we will see here. For example, also you can see the holes here from the side of the end plate. These holes, for example, here to adjust the angle of the flap of the front wing. Actually, in reality, these holes can have an effect on the boundary layer that will develop along the end plate, but we will invest a lot of time to mesh this part, and then in the end we will not like see a lot of difference between the two elements. So we have to make sure that our model is really clean, and we have to cut all these details that are not really important in our CFD, but are more important for construction side. Also, we can see here clearly more details, and we can see this like really significant simplification in the suspension system. So here we can see the suspension system with all the details, and like I told you, from this side is the construction model. So we can see that the model is really representing the real example or the real car. But from the other side, we can take all these details together and represent them with a just one cylinder that will give us the high detailed model. Of course, not 100% accurate results, but this will help you a lot to create high quality mesh, because if you will use this representation of construction model, you'll suffer a lot from bad quality cells that will develop over there, because the shape is not the shape is really small, and there is a lot of angles, and there is a lot of sharp angles that the mesh cannot really fit inside these regions. One of the most important simplifications, and we have talked about this a lot during the previous workshops, it's the radiator. Because actually in the real life, the radiator is like created by hundreds of elements, some fins in the vertical and horizontal direction, and there is a lot of elements over there. And as you can see, there is a pipe, there is, I don't know, maybe a pump, or I don't know what is it, but as you can see, the radiator in reality is really complex geometry with a lot of elements. But in CFD, we don't have to run simulation using this model, because this will cost us a lot, and the result will never be realistic. I mean, you will not get the same accuracy of the surface as here using the mesh. So we have to do another simplification of the radiator, as you can see from here. So the radiator here is represented with a porous media, just have creating a three-dimensional shape that will represent the radiator, and based on the porous media that we have covered during the previous workshop. So you can get really, if you have the right setup of your porous media, you can get really close, accurate results and pressure drop compared to the real example, without investing so much time and so much resources to get the same mesh for the construction model of radiator. Another example that you can see here, maybe here we can see clearly that we have a lot of elements here in the suspension system, and we have simplified all these components and all this system and assemble it together in one cylinder that will give you approximately the same results, especially if you are working with the RANS or Reynolds average Navier-Stokes approach. It's better to have really simple geometry. Of course, later if you have some transient effects or transient simulations, maybe you can add another level of details, but not to this point, because this one is really model mainly destined for construction reasons. Okay, so we have talked a little bit about what you have to do, the featuring of the geometry. Sometimes also for the geometries, I forget to mention this, sometimes in the geometries we can see logos and some written things from the side of the model. So this thing, or especially for the tires, there's these logos and also the description on the side of the tire. So we have to make sure that you have to take off all these things, because this thing will add more mesh for your geometry and bed cells for your mesh. So you have to make sure that you take off all the logos and the written things on the tires or any other parts in your car. Of course, here you have to know one thing. So for when you work with the STL, usually you will have like one solid that will represent the whole geometry. And this can create some problems, especially later when you will start to do post-processing or you want to refine in specific regions. So sometimes you can't get like really control over your single part because your representation of the STL is really one solid for the whole body. And what we suggest from experience and from working with, especially if you're working with complex geometry that have many components, it's really important to, when you convert from the STL or from the precise surface, no matter what's your format like STP or any other format, to the STL format, it's really important actually to take every single component as a separate solid. What I mean by this, so for example, when you, you have this car and you want to, so this car, for example, you have created in a CAD software, of course, and you want to convert it to an STL file. So it's really important to do the following thing. So converting every component in different or separate file, so later when you will combine them together, and I think later my colleague Milad will show you how to do this, how to combine elements in the same folder. So when you do this, first of all, you will get control over your pre-processing, so you can refine the mesh wherever you want. And also later for the post-processing, it's really important to have separate elements. So this will help you to post-process or to understand the behavior of your components separately, and you can understand the contribution of every component, for example, in drag and downforce or any other physical scalar or vector or value. So it's really important for you to split your model into different solids, and as I told you, doing this is by creating different solids for every components of your car. So for example, in our model we created a separate one for the rear wing because we want to get like separate results later when we do the post-processing. And also, for example, if you will take the mesh that you will generate on the wings will not be the same, of course, as the mesh created on the body. And if you will have the same solid all over your geometry, you will face a lot of problems because you will apply the same level of refinement all over your body. So it's really important to separate this. First of all, like I told you, for your pre-processing, for your creating your mesh, for applying really the refinement where you want, like for example the front wing and so on. And secondly, for the post-processing later, is really important to separate your elements to understand the contribution of every element in the performance of the whole system. Okay, so I think for this part of the pre-processing, that's all what we have. I hope it was helpful for you. Of course, we will answer your questions later if you have any question about this. And so, like I told you guys, we have prepared. Yeah.
Just one thing, we have some questions related to the CAD stuff, so I think it would make sense to answer them right now.
All right.
Okay, then let's try. Just 1 second. I have to find the question window. Okay, it is here. By the way, we have a new feature we can test today. Right now it should be possible that you ask your question yourself. I'm not sure if it will work. So let's just try it out, and in the case it's not working, we will just read them out loudly. Okay, the first question is by Eva Maria, and I will now try to unmute her. Eva, can you hear us? Hello?
Hello, maybe you can...
It seems like she has not a headset, so I will read it out. So Eva said she has a problem with her intersection that they did in purpose. Their side wing gets fixed at the monocoque and the side box have holes where the profiles of the flaps of the side wing go through. So we have a purpose intersection, no CFD like. How can I fix this problem? because we have our sidebox as an open space and simulates them too. Okay, I'm not sure if I got the question right, Akram, but I think the problem
I have to imagine it first, or probably if she can send out like picture, that will be great, because these things, it's really important to imagine how your geometry will looks like to really find the solution for the pre-process.
I can imagine. I can imagine what the general problem is.
Tell me.
It's about intersections maybe. So let's say, for example, if you have, guys, listen, if you have, for example, a front wing, and the front wing is, Akram, can you maybe show a picture of the front wing? The picture of the front wing with the pillars.
Okay, let's go back. Here?
Okay, here, exactly. And guys, just imagine this pillar, maybe Akram can hover over it with his mouse. This pillar needs to be somehow connected with the monocoque as well with the wing. And now the big question is, where we have intersections, if you would isolate these parts, just imagine the front wing is a massive part, closed body, the nose is or the chassis is a closed body, and this pillar is closed. And then if you want to intersect it, you don't need to add any holes somewhere. Holes will be generated automatically. So guys, please don't create holes where intersections are, just let the parts intersect. The only thing you have to make sure all the time is that every single, let's say, part is a closed body. If we take a look, for example, at the master model slides, that will become, I think, a little bit more obvious. What you can see here actually is every color part has a different color, and every of these parts is the closed body. And as long as all the subparts are closed, everything will work. And maybe just one last thing I will add, since we'll talk about this master model. The best thing is to create a model out of solid bodies, or at least which are watertight, then export every part as their own STL file, and then merge all STL files into one, which means we will just copy them all into one large file. The reason is, at SimScale right now you can only upload a single STL file, and a lot of CAD tools cannot handle STL files with multiple geometries on site, so therefore this is the best workaround. But we will write a step-by-step tutorial and provide you with it soon about model import together with the homework assignment. Okay, then next question is by Justin. Maybe let's try it again. Let's hope Justin have a headset. So, wait, where is here? Okay, let's see if it works.
Hello, Justin. Can you hear us?
Justin? Justin has no headset. Okay, but Justin's question is, how detailed the meshes are from cars designed by actual automotive companies? And I think he also wants to know about the detailness.
Can you repeat, please, the question?
How detailed are meshes from car designed by actual automotive companies?
So what I know, so for automotive industry, they really use like real cars with a couple of hundreds of cells, even more, because in automotive industry they are not really interested about like simulating aerodynamics only, but it's multidisciplinary in the main time. So they simulate everything together. This include the cycle of the engine, the cooling system, sometimes also the heat transfer between the components, and on top of that also the external aerodynamics. And there is a good article about Mercedes-Benz the last time. They did also in this simulation the internal like HVAC inside the car with the external and all the components. So in automotive industry, they really they use the full model, like the same. Of course, their models are more complex, but they use models like these ones, and they just do it really realistic models with a lot of millions of cells, and probably just to, because we have point this because major automotive industry, they don't use like the CFD tools that are based on the Navier-Stokes equation that require mesh and so on, because the most important thing why we need to reduce the details of these geometries is because the mesh. So there is other softwares that based on other approaches, they don't need to create the mesh, so that's why they go for the full.
Yes, I mean, basically, what Akram wants to say, I think, is that they have different approaches. Automotive industry is mainly looking at aeroacoustic, other phenomena, and but generally spoken, they also use very much simplified models. Just imagine you have a full Porsche 911 model, let's say. I can imagine you will have more than 5,000 screws you have to remove first.
Yeah, of course. Yeah, of course. I mean, this simulation of the high details, it's just the last point in the development process. But the first stage of the development process, you have to make your model as simple as possible, because you will iterate in your design and you will simulate and you will change a lot of things. So we will not go for the high detailed model and then you will change it, and the high detailed model can cost you 100 times than the simple model. So it's better when you design the first step in the design or the first step in your optimization process, take it simple as maximum as possible. Then you can maybe, as a last step, you can add some details that will not affect your mesh quality. Because if you will add details, then you will end up with bad cells and bad quality mesh. It's better to keep it really simple.
Great. Next question is by Mislav. He said, in your formula model, why is the front part shock absorber component, I believe, open completely? Isn't it easier to keep the body closed? Mislav, that's a very good question. Honestly, we have not designed this car. It was designed by, maybe Akram can show the image. The car was designed by the S3 team from Siegen, and I'm quite sure there is a reason why the shock absorber is outside. I can remember from our time in motorsport that sometimes you want to have, you know, some specific geometries for your suspension design, and then it can make sense to keep these parts outside. And what we did in the end, this is very much related to the question before, I think. We just saw what makes a difference. Basically, it's that there is some cylindric body in the near of or here. And then we replace this whole spring assembly by this cylindric body. And I think that's really the point here. Next question is by Venkata, and that's a very good question. How do we debug the problems in any CAD model? Venkata, I would suggest, once you want to get started with SimScale for your own CAD model, first of all, simplify your model. You should not use the same model you use for manufacturing later on. And what you should do basically is, what we did, take the model, redesign it from scratch using existing, for example, you can redesign the model from scratch, which is sometimes easier than delete everything. And then two very important points. First of all, make sure that all your parts are watertight. And if that's the case, there should be no problems with your CAD model. Next question is by David, but was also asked by Eva Maria and Shivansh. It's about basically which formats you can use. Guys, as you know, on SimScale, you can upload IGES, step files, as well as STL files. Nevertheless, we strictly recommend to upload STL files only. The reason is the meshing tool we are using is SnappyX Mesh, only accepts STL files as an input. If you upload your model as a step file or an IGES file to the platform, it will be converted automatically into a STL file, and then you have no control over the tessellation of your STL file. And therefore, I suggest to do it manually in your own CAD model. And very important is then that if you export this whole model with all parts as one STL, 99% of the cases, all faces will be fused together to one. Therefore, you have to export every patch independently and then merge the files later on. Next question is by Aaron. Do you recommend starting with a fully detailed model and then making it simplified, or recreating a simplified model from scratch? Aaron, that's a good question. I think Akram is the best one to answer it since he simplified the model you can see right now. So he started with this complex model on the left side and created this simplified model. So Akram, what would you suggest?
Yeah, for me personally, like I suggest from my experience to do it from scratch. So if you have time, if you can do it quickly, do it from scratch. Because why? You will spend more time. Of course, I'm gonna say the truth. This model we have not modeled from the scratch, but we have just like modified some points and simplified some points. But if you have like time and to do it from scratch, it's better to do it from scratch. Why? Because first of all, the time that you will invest in cleaning up this high detail geometry, and the high detail geometry, for sure you will have a bunch of problems over there. So you will spend a lot of time trying to clean in this geometry. In the meantime, you can do it better by starting from scratch in your CAD software. So for me, I will suggest just to create the CFD model mainly in CAD for CFD. Like you will not go for the construction then move back to the CFD. It's better to start, and of course it's clear. So if you take the development process, you will not create construction model until you validate like a good design. So you will not go for this step of having all these details and all these components until you make sure that your geometry will operate in good way. I mean, you have first to optimize your shape, then you will go for this part. So
Absolutely.
I believe.
Maybe,
Yeah.
Akram, one less, I cannot say which company, but I worked also in F1 before, and there we had the same approach Akram is talking about. So we had, basically, we started with the CFD model, and at once we were sure about the design, we created the construction model based on this CFD model. But unfortunately, we have to continue because we have a lot of more questions and not so much time.
That's right.
But if you have questions, write them in the forum, and then we can come back on you there. Nisha wants to know if we can do surface repairing with SimScale. No, we don't have any surface repairing features, but it's basically not necessary. Since honestly, if as long as you work with STL files and your model is closed, there should be no need for surface repairing. You should do everything in your CAD system. Okay, and next question is by Varun. If the suspension arms have a significant effect on CFD or if they can be removed for the simulation. And that's a good question, Varun, and that's basically a question we cannot answer for you. You have to decide on yourself. There are a lot of strategies. In my opinion, I don't expect to see a lot of difference removing the suspension bars. Not a large, but if you argument like this, you can really remove nearly everything. You should, in the end, every one of you should later for his team find a way they want to go and work right this approach. But if you have no idea how to start, I think the setup we have created and the level of detail we are using should be a good starting point. So like have simplified suspension bars and also have simplified rims. Next question is by Sebastian. And maybe let's try last time if Sebastian has a headset. So maybe because he has a longer question, maybe he can explain it on his own. So Sebastian, can you hear us? Can you say something? Do you have a headset?
Oh, guys, the next time you have to bring
Okay,
headsets.
next time nobody has a headset, so let me read out the question. What is the best way to fix problems with the mesh of CAD models that belong to other company? Is there any way to transform the mesh into a functional model, or do I have to rebuild it on my own, like rims, etc.? Sebastian, I think I know what you're talking about. It's about importing third-party components, right? For example, if you have a supplier for the rim, he will give you a CAD file of his rim. And usually, this kind of models are never provided as STL files. They're usually provided as precise CAD models. And we would suggest make everything you want in your own CAD system, and in the end, then redesign it once you want to export it. So in this case, for example, if your supplier gives you a model of the rim, it will be very complex, have a lot of screws. I would suggest take this model, simplify it, or create even a new model based on this from scratch, and yes, then add it. Okay, I hope this answers your questions, Sebastian. And if not, just reach out to us on the forum. Okay. Nisha asks, if each part is defined separately, how does the assembly of all that components take place together with the CFD platform? Do we define a coordinate system? No, that's very important, Nisha. STL files have an absolute coordinate system. Akram, can you maybe go back to the slide about the STL file format? Perfect. If you write out a single STL file, it's like, and that's what Akram was talking about when he said you lose topological information. STL file, there cannot differentiate between it's a solid, a face, or even just a part of a face. And our concept is, also for model maintenance later on, that you like make an assembly, for example, of all the parts you need of the car, like the front wing main plane, end plate, etc. Then you export every part as their own STL, which will give you such a file. And before you upload them, you merge all files together. I will show you later on how this can look like during when I present the homework to you. And now a question by Thomas. Does the element size in STL tessellation affect in any way the mesh element size? No, Thomas, in theory not. Mesh size is only defined by your dig, but if, let's say, your STL tessellation is coarser than your mesh, you will have still, you cannot increase the mesh size furthermore then, which makes sense. I hope you got it. Okay, then there is some questions we will answer later on, so keep your questions. We'll have the next Q&A session with Nick Perrin just in some moments. And now I think Nick can join us for our design study and give some comments on what we've done. So let me just see if Nick is here. Nick, can you hear us?
Oh, hi, Minat. I'm here.
Yes, great. Thank you very much for joining. And Akram just prepared a design study, which you will present right now, and maybe you also have some things you would like to mention about this, the images you see, and later on we will have the Q&A with you. So Akram, Nick, the stage is yours, and yes.
Okay,
very much.
All right, perfect. Thank you so much, Nick, for joining us. It's a big pleasure for me to be here with you today. So what I'm gonna do, I'm just gonna give like the idea about what we did, and of course we really appreciate your comments, your expert comments on the following slides. So for today we have decided to do like design a study for the front wing. So what we did based on the previous front wing that we had, maybe you have already simulated this front wing, we have decided to create 3 more different designs, and our main target was to increase the downforce maximum as possible, because I believe that in Formula Student the speed is not so high, so drag is not that important, but mainly because there is a lot of curves in the track and so on. So I believe that increasing the downforce can have more important effect on the performance of the car in the track. I hope Nick can agree and maybe can give a comment about the Formula Student aerodynamics, like just in terms of drag and downforce and so on.
Yes, Akram, thanks. I have to say I don't have much experience with Formula Student myself, but like every racing car, you have to work out how much downforce versus how much drag you can put on the car. I think I agree with you, these cars are mainly used in cornering, so you would imagine that you can put downforce at a low ratio, so even with drag, and that wouldn't be an issue. But this is something that you would have to study, knowing the track you are racing on. So that would, require a separate study of lap time simulation and work out this ratio.
Okay, perfect. That's really good to know. So, guys, we have based our simulation on the same setup that we have used in the previous homework. So the same setup, we have just changed the front wing of the different cars. And as you can see, so our baseline was mainly designed, I believe, for medium downforce configuration. So what we did, we have tried to increase the downforce, and of course increasing downforce will be achieved by increasing the elements on your wing, or also adding some extra elements on top, like cascade elements. I believe that cascade elements are more used for controlling the flow over the front tires, and actually from the results we have seen that the cascade elements can reduce the downforce that you will generate with the front wing. And probably also Nick can have a comment on this one, if really the cascade elements will reduce the downforce created by the front wing, but you will get more performance in terms of controlling the flow over the front tires.
Yes, that's right. It will be very much a case by case. It will depend on where the tire is relative to the front wing. These tires are quite small on the Formula Student, so it would be interesting to see if these cascade elements will work as they will on Formula One car, and maybe they wouldn't. So it's something that we'll have to check in CFD.
Yeah, that's right. So what we did here, so let me give you like maybe quick idea about what we did in this design. First of all, we have redesigned the end plate completely, and we have introduced this concept of the foot plate on the end plate, because the idea is, guys, you know that vortices will create when the air try to move from high pressure region to low pressure region. And what will happen is, because here from the side we have maybe atmospheric pressure or a little bit more, because we have this shape of the end plate that will create a little bit of pressure over here. So we have high pressure here from the side, and we know from the lower side of the wing we will have suction effect. So what will happen is you will have some air that will try to move from here, from this high pressure region to the low pressure region under the wing, and this will create vortex, but also will reduce the suction effect under the front wing, and this will reduce the performance of front wing. And that what we did here, we created this foot plate where we will create kind of vortex that will create here in this, I don't know if it's really clear for you, but there is a tube over there. So half of tube that this vortex will be created here, and will take this way and will not go inside the front wing. So also for the other front wings, what we did, we have, so like I told you here, we tested the idea of adding cascade elements to see if the cascade elements actually can add more downforce to the front wing or not, or can reduce the performance, or I'm talking not in terms of performance, but will reduce the downforce that will be created by the front wing. So the other designs, what we did, we increased the number of elements, because you know, if you want to increase the camber of the front wing, you have, or any wing, you have to increase the elements, otherwise you will have rotation flow and you have supination and your wing will stall. So it's really important, if you will increase the camber, you will increase the number of elements as well, to make sure that your wing will work in the right condition. What we did in this last design is, it's the same here with 3 elements, but we have added another element on top here with another end plate from the inner side. So this will help us more to keep more high pressure flow on top of the wing from the sides, because otherwise the flow, because without this interplate here, the air will escape from here to the end of the nose, but when we create this interplates, we will have more high pressure on top of the wing with the extra element. We have also some elements here from the side, and also we have a flap, or I don't know, it's not flap, but a fan on under the wing to reduce also to because we want to do this because later in the cornering it's really important like to have a good balance on the wing, and based on what we have seen the last time, I believe that these fins under the wing will help the wing later for turning. Of course we are not simulating side wing or turning curves, but this concept can help also in keeping the same or homogeneous distribution of the pressure and the front wing. Of course, Nick, if you want to put any comment on this designs, you're welcome.
No, I'm very interested to see the results.
Okay, cool. So let's
I guess like everything, it's all about testing and seeing what's working as well. But,
yeah, that's right. Exactly.
And I'll show you a bit later maybe some of the philosophy we apply on the Formula One design as well.
Okay, perfect.
Once we've seen that presentation.
Okay, great. So let's move to the next slide. So here we have run our simulations, and we can see from the left side to the right side the baseline to the last design. So just to remind you, so here is the baseline, which is like medium downforce configuration front wing. Here we have added the cascade elements. Here we have 3 elements in the front wing, and here we have 3 elements on the front wing with another element on top. And let me give you a really nice analysis, and of course Nick also can comment after this on the front on this result. So first of all, we can see here that the suction effect on the front wing is low compared to the others. So we can see that, for example, the second design where we have used 3 elements, the suction effects is really high, and the pressure here is really low. This will help to suck the car more and to push it more to the ground, so this will give you more downforce in the front. So what we can see here also, because we have redesigned, also one really important thing that we have to show, we have redesigned the shape of the, so let me go back here. So if you can see, we have redesigned the shape of this element here, or the middle part of the front wing, in a way that will push more air under the car or under the front of the car, and this will help the diffuser and also the underbody to create more downforce. And as you can see here, this part is more shaped with the shape of the nose, and we can see that we have more section, and this will help more the front wing to or the car to create more downforce. But let's back to another point that I want to tell you guys, and I have mentioned before, is if we can see between the second design and the third design, I told you that we have decided to create this inner end plate to keep the air on top of the wing here. So this will create more pressure and will help the car to create more downforce. That this air will push the car more to the ground. And if we can back to this slide, we can see clearly that, so this one we don't have, for this design, the second new design, we don't have the inner end plate, but for this one we have the inner end plate. And we can see clearly that here we have more section under the nose more than this design. Why? Because in this design we don't have the inner end plates, and actually the pressure on top of, or the air with high pressure on top of the front wing will escape with high velocity under the nose, and this will create more section. But when we have create this inner interplates, we can see clearly here that the section have been reduced, but we have kept it more high pressure air on top of the the front wing. And also we can see clearly that this, what we did, have an effect on the diffuser. So we can see the diffuser for this one here, especially for the outer side of the diffuser, create more section here than this designs here. It's clear. But also redesigning the front wing have an effect on the rear wing, and we can see that this rear wing has lost some performance compared to this one here, because here, as you can see, there is more section than this one here. And of course, I really love to get the comment from Nick, if it's possible.
Yeah, no, it's very interesting. I think these plots are showing quite well what's happening here. Obviously, we are missing the information of the potentially of the balance of the aerodynamic as well, because the main attribute of the front wing is to change the aerodynamic balance, and I guess on this car you want something close to 50%, or you want, you know, a distributed aerodynamic downforce between the front and the rear of the car.
Yeah, that's right. We have later, I think, in the last slide, we have results about the balance. This will give us more details about the performance of the car. So let's move to the next slide, where we can see the distribution of the pressure back from the top side this time, because the previous slide was the pressure from the air side, where we have section effect, but from the top we have high pressure. And what we can see, so first of all, this is our baseline. You have already worked, guys, on this design, and I think you know this design better than me because you have run multi simulation on this design. So this is how the pressure distribution looks like from the top. But if you will if you'll take a look on this wing, like I told you, the second wing, we have created the cascade elements, and we can see clearly, and I know this from my previous experience, but here is really clear that the cascade elements actually are used to control the flow over the tires and will not really help you to create more downforce, because first of all, the elements are really small, so they will not help you to create downforce. But in the other side, for example, here we have like small tires, like Nick have already mentioned. So the small tires will not have huge effect on the performance of the car, and also the speed of the car is not really high. But what we can see here, using these cascade elements, we are losing a lot of pressure from the upper side of the wing. Why? Because we have an acceleration of the flow under the cascade elements, and this acceleration will reduce the pressure on top of the front wing. And you can see here clearly that we are losing a lot of high pressure from the top of the wing, as well for the flap, because we will have like disturbed flow, or the weight of the cascade elements will affect directly the flaps, and this will create problem for the front wing design. So maybe later, or the next step, when you will take your design for new front wing, you can take this point in consideration, that the cascade elements will really reduce your performance of the front wing in terms of generating downforce. Let's move to the next design, which is the second new design, where we have created a wing with 3 elements. And we can see clearly that this wing generates really high pressure from the top, especially in the second and the third element of the front wing, which is the flaps. And I believe this because they face the free stream, so that's why we have high pressure over there. And for the last design, we can see that we are losing also some pressure from the top, and that's because if I will back to the design slide, so like I showed you, we have created this elements here. So our idea is to add some downforce for the front wing, but actually this have reduced some downforce for the wing. Why? Because this element is relatively small compared to the main wing, so if so this element will generate downforce, but the downforce that will be generated by this element is really small compared to the downforce that we have lost by creating this element on top of the front wing. So we have to take this in consideration also in designing our new designs, and as you can see, we are losing a lot of high pressure here, and this will reduce the high pressure on top of the wing, and in consequence will reduce the downforce created by the wing as well. Of course, Nick, if you have any comments, you are welcome.
No, it's all clear. It's all good. Carry on. Just to see I'd like to see the aero balance and the downforce level if we can.
All right, perfect. So let's move to the next slide. So here from this slide, because from the previous workshop, you have learned, guys, how to post-process which quantity you have to look for. So here we have make it really important quantity when it came to understanding the flow over a car or over an object, because here we are looking to, so in terms of energy, we are looking to the kinetic energy. So the kinetic energy of the flow, it's represented, we can say, with the total pressure. So the total, so if you have, so where we have like a red region, it's high kinetic energy. So where we have the blue spot like this one here, we are losing energy over there, and it's important to look to your design in this point. And we are doing this slice here of the total pressure of the front wing and the tires, and we want to see the effect on our new front wing designs on the tires. And we can see clearly that, so for the first one, the first design, or the baseline and the first design, especially for the baseline, the flow is more smooth over the tires, so the width of the tires is not that big, because the size of the front wing is small, so will not disturb the flow that will go to the front tires. Of course, here by adding these elements for the cascade element, we can see that also we have separation of the flow on top of the wing, because we have suction effect here and in between the cascade elements and the front wing, and this acceleration will take more air upward, so that's why we can see that we have separation over here. And if we move to the next car, where we have the 3-element wing, we can see clearly that the width of the tire is huge, and this is because of the effect of the front wing, because this front wing will have like really strong or really disturbed wick, and this will affect directly the front tires, and we can see clearly that the wick of the front tires is really significant here, and we are losing a lot of performance here, and the drag of the created by the tire will be remarkable in the results. And also the point of rotation or the separation of the flow, it's really clear of the tires is affected by the front wing. I think Nick, of course, can give better explanation here, because I think in Formula One they're really into this thing. So please, Nick, if you can give us a comment on these slides. I mean, compared to what you're looking for, maybe explanation on the separation over here, also this blue spot here in front of the front tires.
Yeah, I mean the separation at the top of a wing element in this case is not necessarily significant in terms of an issue. You want the flow to be clean, but it's not always a problem if you've got some small separation at the top. You'll find that when you play with a front wing, you don't always get, you have to look at the overall force at the end, because if you get more downforce, less drag, it's better. And at the end, that's what you want. The explanation of the flow through the front wing is interesting to look in parallel to the forces, but it's not always directly linked to better or worse, if you see what I mean. So it's such a complicated rotational flow. The other thing that you want to look at with front wing is you want to make sure the flow to the diffuser is clean, so you want energy going to the diffuser. So if you imagine the flow coming from the front to the back of the car, and you've got a set amount of energy, which is the velocity of the car and the density of the flow. You don't want to spoil all that energy just in the front wing, because then nothing is left for the back of the car, if that makes sense. So that's why the front wing needs to remain to a certain size, but not too big. Otherwise you spoil overall energy, and what is created in the diffuser is going to be less downforce, less efficiency. If you think of the front wing as well, it's a less efficient component compared to the diffuser.
That's right.
The downforce to the drag ratio it generates is less efficient than diffuser. So you want the diffuser to work harder on the front wing if you can, as long as your car remains balanced, as long as effectively you are close to your aerodynamic balance target of 45%, for example, at the front and 55% at the rear. So depending on the balance you have, you know if you need to work harder or less hard your front wing. So it's a little bit of a balancing act. So the front wing is a complex piece of geometry to develop. If you think of the rear wing, there's nothing behind, so you can push it as hard as you can. But if you think of the front wing, there's a full car behind it, so you have to be really careful with what you're doing.
All right, that's great. That's great to hear. So just like small comment on because here in Formula Student, and for me personally, it's my first experience with Formula Student working. And yeah, actually, according to the results, we have seen that the major part that generates downforce is the front wing and the rear wing, and I think this because the speed is really low. I think for our simulation it's 20 meters per second, and actually I think, I don't know if you agree with me or not, but at this speed the diffuser will not really have huge effect or will not work at low speeds. It's better when you move at high speeds, then the diffuser can have an effect, and this is according to the results that we get. So for example, the diffuser generates sometimes like 20 or 30 newtons instead of the front wing, and the rear wing generates around 200 newtons.
Well, this shouldn't be dependent of speed. This should be independent of speed. If the wings are generating 80% of downforce, it will be the same at any speed. And I think what happens with the Formula Student, it's got a huge front wing, it's got a huge rear wing, and actually quite a small diffuser. That's coming from the regulation, I expect. And where if you look at a Formula 1 car, the diffuser floor will generate probably 50 or 60% of downforce.
Yeah, that's right.
From the wings.
Right.
So I guess it comes from the regulations, which in this case means that yes, you can probably push the front wing more because you will spoil the diffuser, but it's less of an effect. And the rear wing is still high, so it works independently, I guess.
Yeah, that's right. And also here the design of this cars is completely different from the Formula 1. I can't really see. So yeah, you can see here that the diffuser is working only in this region. So here it's like the floor of the car, and unfortunately we don't have diffuser here. So the diffuser is just this region here. It's really small compared to the front wing and the rear wing, and probably it's because of the regulation, but yeah, that's why I think the diffuser is not really giving the same performance in Formula 1 or in other like automotive aerodynamics categories. Okay, so let's move to the next slide, which is, I think it's really good slide to see. Maybe you can't really figure out where is the part here. So here we are really behind the front wing and in front of the front tire. So if I will back here, so this slide is just here. So if we create slice over here in this position between the front wing and the front tires, so we will see this pictures or this images over here. So we can see that for our small front wings, so like the first one and the second one, we can see that the width of the front wing is not that big, so you can so the effect of the front wing on the rest of the car will not be as really big in terms of kinetic energy that will go to the back of the car, or the flow that will go to the back of the car is more cleaner than the new front, the two last front wings that have 3 elements. And as you can see here, the front wing with 3 elements create more disturbance in the flow. But what we can see here, which is, I think it's nice to see, so like you can see here, we have this vortex over here. This one is created because of the fin that we have created under the wing, and we can see that this fin reduced a little bit in the size of this this red or low energy flow that is here. So this can be investigated maybe in more details, but it's good to see this point that this fin reduced the size of this blue spot of low energy in the flow. Of course, Nick, if you have any comment, you are welcome.
Well, just to say that obviously these plots are showing very well that the bigger the front wing and the worse the energy going to the back of the car, because there's less and less red, so it's pretty clear. And which is why, again, you have to be really careful with pushing the front wing more. You need to make sure that it works with the way you want to balance the car, because you will lose rear downforce for sure.
Mm-hmm. That's right. So let's move to I think the last slide, but maybe we'll run out of time, so I'm gonna make it snap a little bit. So here we can see the pressure distribution from the side. So the same slides that we did in the previous slide for the total pressure, but here we are doing the pressure. And what we can see, mainly what I want to show here is the distribution of the front wing, the pressure over the front wing, and how this distribution changed. And let me show you something here which is really important. It's the ground effect, because we have changed the height of the front wing to give it more suction effect, and we can see this significantly here, how changing the position of the front wing just a little bit can have huge effect on the downforce created by the front wing. And here, maybe here you can see this clearly, the thing that I was talking about, how the cascade element will reduce the pressure on top of the front wing. And as you can see here, we can see clearly that there is acceleration of the flow under the cascade elements. And actually we can see here in this baseline that the pressure here is really high, but here we have just like really low quantity of pressure on top of the front wing, and this is because of the suction effect on under the cascade elements. So this will reduce the pressure on top of the front wing. So also another point, it's the same comment here about this element that we have, put it on top of this wing, and actually this reduced the pressure on top of the wing more than creating downforce. So from now, guys, make sure that you take in consideration that adding any element on top of your wing, this will create a lot of or will reduce the pressure on top of the front wing, because you will have a suction under your element or cascade element or any kind of element that you will add on top of your wing, and this will reduce the pressure on top of the wing, and in consequence will reduce the downforce. Okay, so I think it's the last slide where we can see some velocity distribution, and it's clear that we have seen this before with the total pressure, and here with the velocity profile, and we can see clearly that the front wing will create big front wing will create more downforce locally, but will disturb the flow in the back. So you have to take this in consideration the next time when you design your car. It's dependent on what you are looking for, efficiency or more downforce. If you want more downforce, make it bigger, because the downforce is function of the surface. And if you want to make more efficient car, so make sure that you will make it smaller with more. I mean what I mean by smaller is more smoother, and the flow is more smoother behind it. Of course, I think it's the last slide probably. Maybe Nick can give like comment here over this slide, and we can move to the last slide of the. I think the interesting thing for Nick, it's the forces on the car.
Yeah, I'll let you continue then to the next slide, no problem.
Okay, so the last slide, it's the forces. And yeah, I think for these forces we have only the front wheel and the front wing. Unfortunately, Nick, I'm so sorry for this, we don't have the rear wing, but I'm going to send it to you to make sure that we will have a nice comment on the forum as well. So here we can see the pressure distribution, the lift or the downforce represented by the blue ones, and the orange one represent the drag. And for this is the front wheel, because our idea was how the front wing can affect the front tire, and we can see that actually the second design reduced the drag significantly, and this is because of the cascade element. So guys, I was really surprised about this result. So you can see clearly that the cascade elements, that's right, that the cascade elements will reduce the performance of the front wing, will reduce the downforce created by the front wing, and you can see this sorry, I'm mixing the designs, guys. So this design, so I was thinking it's in the right distribution, but no. Actually, this is the second design where we have the cascade elements, and we can see clearly that we have losing a lot of downforce over here. I'm so sorry, guys, for this mistake, but just because I didn't notice that we are in the second design here and not the first one. So here we can see clearly that the drag force being increased. I think because of the cascade elements in this time, and also the shape of the front wing. But at the same time, we are losing a lot of lift here, and this is because of we are losing a lot of lift because of the cascade elements, and we are losing pressure from the top of the front wing. So if we will move to the second wing, which the results looks a little bit strange. I'm gonna check it, but looks like the pressure, the downforce, and also the drag have been reduced significantly, and I think that this is because of maybe this front wing is more efficient on the tires, so this can control the flow of the tire around the tires better. And I think it's because the front wing is really large, so this will cover a big portion of the front tire, so will reduce the drag created by the front tires. And like you know, guys, for the tires,
Akram,
I think, yeah.
I'm very sorry, but we're really running out of time.
Okay, so maybe Nick can give a quick, sorry guys, and sorry Milad, but maybe Nick can give comments better than what I'm doing. If you can give a comment on the following plots that we have.
Well, quickly speaking, first of all, the front wheel forces are really small. I mean, we would have to have the same scale on the left and right plots, and actually, relatively speaking, they're really small compared to the front wing itself. And again, I think we'd have to look at the full car to draw a clear picture of which design would be better. But I think it's quite logical to see more downforce coming on the front wing from your from design 2 and 3. So I think it all makes sense.
Okay, good guys. So I will make sure, guys, to put a good commenting on this part of the slide. I'm sorry, but we are really run out of time. So let's move to the Q&A session. And yeah, I think Milad can take this here.
Yeah, thank you very much, Akram. Let's make it quick. First of all, let's talk about your homework. You may notice we didn't have a live demonstration so far. The reason that at this time we will put the focus really on utilization of simulation. So your job for the next homework is to redesign your own front wing and perform a CFD simulation. So therefore, first important step is you have to design a new front wing using a CAD system. Since you're all participating at Formula Student or Formula SAE, I think you know how to use CAD and you have access to such systems. If not, we can also recommend to use a free online CAD tool, and we will put all this information together into a step-by-step tutorial, by the way, and put it to the forum during the next days. Once you have designed your CAD model of the front wing, you have to export it as single STLs and merge it with the existing car. So we will therefore provide you with a car model which has no front wing, and then later on you have to merge it. And the final part is to run the simulation according to the instructions of session 2 or session 2. But don't worry, we will launch we will publish this homework assignment during the next days, and we will also extend the deadline since it's Christmas. Just one final thing, just to show you what I was talking about when I referred to model structure. So this is basically how the model is looking like when you were exported from a CAD model. So we have for every patch a single STL file. For example, here the front wing main plane, it's a single file which is water closed, and the only thing you have to make sure everything is in the same absolute coordinate system. And what you can do then to merge files, for example, is let's for example open the front wing flap in the text editor, and here you can see this is a text file. And if we want to merge them, we have just to copy all the text files together in one text file. We will therefore provide you also with a little tool, a script, which will do this automatically. Okay, guys, then thank you very much for being here with us. We have 2 questions, or 3 questions, which are not answered yet. So maybe Nick or Akram can help. First of all, is how to decide on the height of the front wing so that sufficient energy is available in the diffuser for generating downforce. Maybe Nick can answer to this question.
Well, that's a really good question, and I think it will have to be one of the first questions you're asking yourself. Because first of all, I don't know the regulation, but there could be a box anyway, so there could be a dimension you cannot go higher than, so we'll have to check that. But the other thing is we'd have to decide, do we want more front downforce or more rear downforce? Where do we want the balance? And that has to be a really important decision to be made. I mean, obviously at that point in time for that project, I'm not sure if we can make that call. If we purely want to generate more front downforce on the front wing, obviously the answer is to go as big as you can. But it's not as simple as that. We'll have to see if there is a limitation by the regulation.
Okay, great. Then we have some other questions. Also, Vanja, who wants to offer an explanation for the second front wing design. Unfortunately, really running out of time, so I would ask you, we will prepare a written documentation of this design study, and then we can discuss about it. Okay, guys, thank you very much. Thank you very much, Akram. Thank you very much, Nick, for being here. It was a great workshop so far, a lot of participants, and yeah, thank you very much, and hope to see you all very soon.
Thank you, everybody. Have a nice evening.
Thank you. Cheers. Bye-bye.
Okay. Bye. One thing, guys, don't forget to submit your homework to qualify for a pre-professional subscription of SimScale for your team, for a certification for you. and for sure for massive support for your team. If you have questions, use the forum to reach out to us. See you soon. Bye.